For this video, we're going to talk about solving radical equations. And just like we did with the rational ones, we'll work through a couple examples, which are sample homework problems. But first, I'd like to point out that the reason these are called radical equations is that they contain radical expressions. So looking at this example here, the square root of x squared plus 1 is called a radical expression because it has an algebraic expression underneath a radical symbol, okay? And you'll notice in the first example, number 22 from the homework, there are two different radical expressions. In the second example, there's only one. So both are examples of radical expressions. So the idea of solving radical equations. So the idea is really simple, but there's something to unpack there. The idea is get rid of the radical by squaring both sides. Okay, so this seems like a pretty straightforward idea, but let's unpack a few things. So the first thing I want to do is I want to put a little asterisk above the word squaring. And I'm going to make a little footnote here. So we're going to be squaring both sides if radicals are square roots. We don't encounter a ton of these equations, but I want to point out all the same that you could have radical equations that have cube roots in them or fifth roots in them or really any radical at all. So to get rid of the radical, you essentially undo whatever it does. So for example, if they were cube roots, we would cube both sides. If they were fifth roots, we would raise both sides to the fifth power. But for our purposes, they're going to be square roots, I think, in all cases. So we're going to be squaring both sides. Now, the next issue is, and I'm going to make this sort of a is squaring both sides allowed? What do I mean by that? Well, what I mean by it is that in our previous example, we were solving rational equations. In our previous lesson, we were solving rational equations. And when we went to multiply both sides by the least common multiple of the denominators, we had to be careful because we needed to make sure it wasn't 0. And so I want to think about the same sort of thing with squaring both sides. So will squaring both sides preserve equality? So I'm going to take a second down here, and I want to ask you the following question. If A is equal to B, is A squared equal to B squared? Okay, so if we have two equal numbers, are their squares also going to be equal? The answer to this question seems pretty reasonably yes. If you take the same number on both sides, whether it's 4 and 4 or -7 and -7, when you go to square on both sides, you get the same thing. So this is good. And that's a big deal because it means that squaring both sides is not going to lose solutions to the equation. So it's not going to take a situation where the two sides are equal and mess it up to where they're not. But here is kind of another side of that coin. If two things are not equal, is it possible that squaring both sides makes them equal? So in other words, can you think of two numbers that are not the same number, but they have equal squares? So I can't see your faces, but I'm kind of hoping that you're noodling on this right now and trying to think of two numbers that are not the same, but they have the same square. And what I hope that you're realizing is, wait a minute, any pair of opposites is going to have this problem. So I'm going to say here, any pair of opposites. So 3 is not equal to negative 3, but 3 squared is equal to negative 3 squared, for example. And any other pair of opposites is going to have the same problem. So why is this significant? It's significant because it means that just because you find that the squares are equal to each other does not guarantee that the original numbers were equal to each other. So when we go and start an equation by squaring both sides, we could potentially end up with what are called extraneous solutions. So for now, I'm just going to leave that said, and then when we start working out the examples, I will show you what I mean by this. So let's go ahead and dive in. So we have this equation, the square root of 7 plus x, and we want that to be equal to the square root of x squared plus 1. And let's go ahead and square both sides. So the nice thing about this equation is that both sides are just lonely square roots. So all that squaring is going to do is get rid of that square root. So on the left, we'll have 7 plus x. On the right, we'll have x squared plus 1. So this is a quadratic equation. Notice how often the need to solve a quadratic equation comes up. So we know how to solve quadratics. We're going to move everything to one side, see if we can factor. You'll notice generally we can. So we'll subtract x and subtract 7 from both sides. So we have x squared minus x minus 6 is equal to 0. Sure enough, that factors into x minus 3 times x plus 2. And now by the zero product property, the two solutions here are 3 and negative 2. So here's what I'm going to say. I'm actually going to spell it out this time. I don't think I'm going to spell it out every time, but I think it's important to spell out at least once. What I just found is that the square of the square root of 7 plus x and the square of the square root of x squared plus 1 is true for x equal to negative 2 and 3. But I'm not interested in knowing when the squares are equal. I want to know that the original statement is true. So what we're going to do is we're going to check to make sure. And I'm going to write the word this time. Neither is extraneous. Okay? So what that means is checking in the original equation before we squared that these two values make up solutions. So this takes us back to what we were talking about in our very first lesson. To be a solution, it has to satisfy the equation. It doesn't satisfy like a modified version of the equation that may or may not be equivalent. It satisfies the original equation. All right, so here goes. We'll do this in green in the hopes that they both work. So checking, let's do negative 2 first. So on the left, we have the square root of 7 plus negative 2. On the right we have, and I'm checking to see if they're equal, the square root of negative 2 squared plus 1. Okay, well, on the right we have the square root of 7 minus 2, which is 5. And on the left, we also have the square root of 2 squared plus 1. That's 4 plus 1, which is also 5. So yes, negative 2 works. Let's see what happens with 3. Okay. And quite quickly, I think you'll all agree with me, this is going to work out also. So the square root of 7 plus 3 on the left, and the square root of 3 squared plus 1 on the right. And sure enough, both of these are the square root of 10. So in this problem, we ended up with 2 potential solutions. Neither one of them ended up extraneous. So there are 2 solutions here, and I'm actually going to go ahead and write them in the blank here. They are negative 2 and 3. So I want to make a few things clear. The fact that one of our potential solutions was negative did not rule it out. It is not necessarily the case that one of our solutions or some number of our solutions will be extraneous. So there's really no guarantee, which is why it's so important once you find the solutions after you square both sides to make sure that the solutions would have worked before you squared both sides also. So now let's move on to our next problem. So for this problem, I actually want to start by looking at the left-hand side. And I want to point out to you that in this particular instance, the radical is not isolated on the left-hand side. If you compare that to the example that we just did, the radical expressions were by themselves on either side. So squaring was actually a really simple, quick exercise. Just the square roots popped up and we could go from there. But here we have this mixture happening on the left-hand side. So without going into too much detail, we always start by isolating the radical, if possible. Now, in reality, it's not always possible to do that, and so sometimes you have sort of a long-winded solution process, but for our purposes, it'll always be possible to isolate. Why not? So I'll make this a very, very brief kind of cautionary statement. If you were to square the left-hand side without isolating the radical first, you would have to do the whole distributing piece. So you would have, you could write it out, and it would be x minus the square root of x minus 1 times x minus the square root of x minus 1, and then you'd have to distribute. And you can see very clearly that you end up with this messy situation where you end up with 2 identical copies of x times the square root of x minus 1. So in some sense, if your goal is to get rid of the radical, this does not accomplish that goal. But if the radical is by itself and you square, that will get rid of the radical. So that's kind of a quick explanation of why we always start by isolating the radical if we can. Okay, so here goes. I'm going to go ahead and recopy. How you choose to isolate the radical is kind of up to you. There's more than one way to do it. I'm going to do this by adding the square root of x plus 1 to both sides. The square root of x minus 1 to both sides. That's going to move the square root over from the left side to the right side. And then I'm going to subtract 3 from both sides. So that's going to move the 3 over from the right to the left. So what do we have left? We have x minus 3 is equal to the square root of x minus 1. Now that the radical is isolated, let's go ahead and square both sides. So we'll square the left-hand side and we'll square the right-hand side. Now, one of the things that you'll notice it's really important to be super, super careful about is that your squaring skills are solid. So remember, when you're squaring something, you're not squaring it term by term, you're multiplying it by all of itself. So x minus 3 squared is x minus 3 times x minus 3. I'm not going to go through the whole distributing process, but I just want to kind of call your attention to the fact that you would be distributing here, and you would end up with x squared minus 6x plus 9 on the left. And then the good news is that you end up with x minus 1 on the right. Okay, so next we again have a quadratic equation. So we're going to set it to 0. Hopefully factor. I guess if need be, we can use the quadratic formula, but it'll actually, I think, turn out to factor pretty easily. So we're going to subtract x and add 1 to both sides, which leaves us with x squared minus 7x plus 10 is equal to 0. And this does factor. It'll factor into x minus 2 times x minus 5. And so by the zero product property, the solutions at this moment are 2 and 5. Now, remember, I didn't write it all out the way that I did in this other example. But what we found at this point is that when x is 2 and x is 5, the squares of the two sides of our equation are equal. But as we saw over here in our mini discussion, just because the squares of two numbers are equal doesn't mean that they were equal to begin with. So just like before, we're going to go ahead and check for extraneous. So check for extraneous. So notice that I am not checking because I want to make sure that I didn't make any mistakes. I'm not checking because I'm a conscientious, organized student, although I am those things, and so are you. I'm checking because I used a slightly flawed process that might generate fake information that I need to be in charge of eliminating. Okay, so here goes. Let's do 2 first. Which version of the original equation you check in, the one after we isolated the radical or the one before? Up to you. I guess you could make an argument for checking the original, just so that you're also accounting for maybe any little snafus you made along the way. All right, so here we go. So 2 minus the square root of 2 minus 1, and I want to see if that's equal to 3. Oh, well, here's our first problem. 2 minus 1 is 1. Square root of 1 is 1. What do you all think? Is 2 minus 1 equal to 3? No. So 2 in this problem is our first example of an extraneous solution. Now the fact that 2 is extraneous, for our purposes, probably means that the 5 won't be, but we should always check to be sure. So let's check the 5. So 5 minus the square root of 5 minus 1. Is that equal to 3? So 5 minus 1 is 4. Square root of 4 is 2. Sure enough, 5 minus 2 is equal to 3. So in this case, we got 2 potential solutions, and only one of them proved not to be extraneous. So here where it's asking us to enter our answers as a comma-separated list, there's only one solution, and that solution is 5. So really quick recap. To solve radical equations, we are going to get rid of the radical by squaring both sides. Of course, that's if we have square roots, which for our purposes we generally will. And then after we go through the process of squaring both sides, we solve the resulting equation, which has no more radicals in it. And whatever solutions we get, we take with a grain of salt. We check to make sure they actually satisfy the original equation, because squaring both sides is not totally equality preserving. Squaring both sides may take two values that are not equal and make them appear equal after squaring. So there could be extraneous solutions as a byproduct of the method. The last thing that I want to remind you of is that when we encounter a radical equation, we always check to see whether the radical is isolated. If it is, as it was in the first example, square both sides, you're good. If it's not, we start by isolating the radical, meaning moving things around so that the radical term is by itself. This concludes our mini lesson on solving radical equations, which should be the last lesson that you need to work your way through homework 1.